So our speaker, Ashvin Vishwanath, is a graduate of the Indian Institute of Technology, Kanpur, where he got an MSc in physics. He was a postdoctoral fellow at MIT. After that, he accepted a faculty position at Berkeley until a few years ago, Harvard recruited him back to Boston. So Ashvin is one of the most creative and influential theoretical physicists of his generation. This introduction would have to be longer than the talk to really do justice to all his contributions. So let me just say that he's let me just say that he has worked on the theory of quantum phase transitions, topological states of matter, and his work is now increasingly draws upon ideas of quantum information and entanglement. Ashvin directs the Simons collaboration on ultra quantum matter and holds a distinguished visiting chair at the Perimeter Institute. He's a Sloan, Guggenheim, and APS fellow, and a recipient of the Europhysics Prize for 2016 for his prediction of magnetic Skyrmion phase, which is a new state of quantum matter. He's also a recipient of the Distinguished Alumnus Award of IIT Kanpur. Ashvin is here today to tell us about superconductivity in twisted bilayer and trilayer graphene. This is really one of the most exciting developments in condensed matter physics in the past 30 years. And Ashvin has generated some of the most interesting ideas about this problem. So we're delighted to have you here, and especially at this very moment in time. Welcome, Ashvin, and the floor is yours.
Thank you, Harsh. And unfortunately, of course, we cannot do this in person. And, you know, for example, I don't think I've ever met Harsh in person before, although we both went to the same undergraduate institution at different times. And, you know, I spent my years there hearing a lot about him and other people who had gone ahead. So I was, you know, hoping this could happen in person, but maybe some other time. So my talk is about Moiré systems, or Moiré lattices, which was really ignited by this amazing discovery which happened, it's hard to believe, just about 3 years back, when people took a pair of sheets of graphene, put them together and twisted them. Okay, and I think this is really a very sort of wonderful example of the way condensed matter physics operates. You take a completely mundane material. This is literally coal, right? You take coal, something as mundane as that, and you know there's technology to extract these sheets of graphene. You twist it, and as I'll explain to you, all kinds of things have been seen, and it's really sort of taken the condensed matter world by storm. And I'll try to tell you a little bit about our theoretical ideas, but hopefully I'm, you know, some of them are speculative. It's early days still in the field, but hopefully I'll convey a flavor of all of the interesting ingredients that come together in this problem, very interesting experiments. There's a potential for technological applications, and as you'll see, there's some very interesting theory that seems to be lurking in these systems. Okay, so by the way, feel free to interrupt me, and you know, if I'm running short on time, I may defer your question till the end. But if there's some clarifications, I can certainly give them during the talk. Okay, so what happens when you take a pair of sheets of graphene? That's the atomic lattice of carbon. Graphene, as you know, is a single two-dimensional material. It's atomically thin, made of carbon atoms element. Basically, you take two sheets of them and then you twist them, right? This is what the experimentalists did. And as you see, you have this Moiré pattern that's generated. And the pattern depends on the angle. I've twisted it by a fairly large angle. So you see the pattern is a little bit bigger than the atomic lattice spacing. And the problem that we will be looking at is that of electrons that are part of the graphene sheet moving through this crystal lattice, this Moiré lattice, the lattice that you see, the pattern that emerges by doing this twist. Okay, and this turns out to have significant consequences for the electrons. But before we get into this problem, let's take a step back and talk about electrons in the original crystal lattice. Okay, and this is a topic that's been around since the birth of quantum mechanics. And once we have a little bit of introduction there, I'll switch back to this problem, electrons moving through this Moiré lattice. Okay, so for a long time, historically, it was a bit of a mystery why certain elements or certain substances are insulators, some are metals. And if you think of electrons as the charged objects, which people kind of knew, how do they get through this forest of atoms, this crystal of atoms? How are they able to propagate right through and give rise to metallic behavior and sometimes become insulating? All of this got clarified with the advent of quantum mechanics, when it became clear that electrons moving through a periodic solid, it's not very different from electrons moving through the vacuum. There's the wave propagation of electrons can allow you to transmit these charges very efficiently when you have a periodic arrangement. And that led to the theory of bands, quantum mechanical bands. So the energy as a function of momentum for the electron is modified, gives rise to these energy bands. And when you completely fill a band, that's one way to get an insulator. That's what happens, for example, here. When all the bands are completely filled, you get insulating states. There's no way for these electrons to move, but if they're partially filled, you can get metals. Okay, that was the understanding that came about. And in a way, you can think of the crystal as being an artificial vacuum. So you filled up all the energy levels, and now you think about excitations. And the fact that you have this crystalline medium can affect those excitations. Again, this has been exploited, as you know, to great effect in solid state electronics. In the old days, people had these vacuum tubes. They were sending electrons across the vacuum. And then, of course, people realized that you could do that as well through a crystalline solid. This crystalline solid could be a vacuum. And for example, here is the band structure of silicon. And by moving through the crystalline potential, you can modify the properties of the electron. You can have, for example, a different effective mass that's shown over here, the parabolic dispersion over here. You can also have holes. You can take out electrons that are in the filled bands and get effectively positively charged carriers, the analogs of positrons, but of course, in this case, at very low energies, without having to crank up your energy. The control and the ability to control these properties, of course, has led to a lot of the modern electronics. And when you think back, how have things changed? And actually, it's interesting to go back to the history of the transistor. There's a very nice book called Crystal Fire that I recommend to think about how things changed. So when the first transistor was debuted and sort of demonstrated, the thing that shocked people was, as in this quote, as soon as you flick the switch, it began to work. And people who were used to these vacuum tubes that had to heat up, they used thermionic emission. You had to wait a little bit till it heated up before your electronics got going. So that itself was an advance. And of course, you can miniaturize, you can control many properties. But you can ask, can you get qualitatively new effects? So electrons inside a crystal are kind of like a new vacuum for the crystal. You can have quantitatively different properties for the excitations. But can you actually have qualitatively new phenomena? And in fact, you can. And one way to think about it is to sort of think about the equations of motion, semi-classical equations of motion. Of course, these are quantum mechanical objects for electrons inside a crystal. And if you look at the velocity, it's just the gradient and momentum of the energy dispersion. This is what I talked about, that you can modify the effective mass inside a crystal. But qualitatively, it's not very different from the usual velocity being the gradient of t squared over 2m. X and k are the position and momentum. The momentum changes as a function of the force applied if you apply potentials. But you get some new terms. Okay, and for example, you have the Lorentz force for electrons. This is present whether you're in free space or in a crystal. But interestingly, in a crystal, you can get another effect. Okay? And the other effect is called the anomalous velocity. There's a term that modifies how the velocity of the electron behaves when you have an acceleration of the electrons. Okay, when the momentum is being changed, the electrons can drift sideways as though there is some sort of magnetic field. There's a dual of a magnetic field present. Okay, so these are actually the semi-classical equations for the most general semi-classical equations for electrons inside a crystalline solid. And in a way, it's kind of pleasing because in free space, these equations lack a symmetry. Okay, they look something like this. They don't have sort of a nice symmetry between the position and momentum space. It's kind of restored when you go inside the electron the crystalline band structure. And you can ask, what is this effective magnetic field? It's called a Berry curvature. Okay, so the Berry curvature, which is really related to how the wave functions of the electrons change as you move around in momentum space. You calculate the Berry's phase of these wave functions, and that is related to this Berry curvature. And that's going to be a fundamental property that is new once your electrons enter a crystalline solid. Okay, so what can this give you? And all of these are going to be relevant for us when we talk about magic angle graphene. So I'm just trying to set the stage and set it in a slightly bigger context than that specific system. Well, one thing this Berry curvature does for you is that it can give rise to certain topological phenomena. And topology, as you must have heard many, many times in talks like this, it's really a property that is robust under small deformations, and it's extremely useful in things like condensed matter physics, because that's how we think about phases of matter. You have a phase of matter, you change some parameter, it doesn't immediately change in a qualitative way. Okay, so topology has the same kind of flavor. For example, one of the early applications of topology was to think about manifolds, two-dimensional manifolds, and classify them in terms of how many handles they had. Sphere would be a genus 0, no handles, a torus. The surface of a donut would be genus 1, this is genus 2, and so on. Okay, and there's a beautiful formula that Gauss came up with. So he had a way to relate geometry and topology. Okay, so he said that if you were to calculate the curvature of any of these objects, the sphere or the torus or these, locally you can define a curvature, and then you can integrate the curvature of the surface. This can be done by someone who lives on these surfaces, and he showed that this will always give you 4 pi times an integer. And the integer is actually related to the number of handles. Okay, so of course Gauss had many formulas, but apparently he called this one many theorems, but apparently he called this one his remarkable theorem, and indeed it is. It also sort of combines his interests in mathematics with apparently his day job was doing these surveying. He had this job of trying to survey the areas around where he lived, and presumably those kind of applications alerted him to these interesting connections that were present. And something very similar happens for our electrons in a crystal. So the analog of this curvature over here is the Berry curvature that I mentioned. You go to the momentum space, it's called the Brillouin zone, the allowed momenta. You integrate over that entire space, and you're guaranteed that this will be 2 pi times some integer. Okay, so this is a connection again here between the geometry of the electronic wave functions and something topological. So what is this integer n? It turns out it's related to something called the Hall conductance, which we'll talk about in a minute. Another way to think about it is in these insulators that have n that is not 0, you will find that although there is insulating properties in the material, if you go to the edge will behave like a metal. So somehow it combines insulating and metallic properties. Okay, so So all of this, these concepts were relevant when, back in 1980, von Klitzing, took a sheet of a two-dimensional sheet of electrons, exposed it to a magnetic field, and measured what's called the Hall conductance. Okay, so you applied a voltage in one direction, let's say in this, along the yellow direction, and instead of measuring the current in the same direction, that's what you'd normally do, he measured the current in the perpendicular direction. Okay, that's the Hall resistance. And much to his surprise and the surprise of everyone else, he found this red curve. Okay, so instead of being just theory would have predicted is just some kind of line, but that line broke up when you go to high magnetic fields into a series of plateaus. And then these plateaus, of course, imply a certain value of the Hall conductance. The Hall resistance over here, which has some natural units. It has units of h over e squared, Planck's constant divided by square of the charge of the electron. And when you converted it into those units, it turns out it's related to an integer. Okay, it's just 1 over the integer times this universal constant. Okay, so this was an example of topology at work. So the topological concepts I talked about before, the anomalous velocity and the Berry curvature, come together over here to give the state of matter where these different integers are really different phases of matter that differ at the level of topology. Another thing that's pretty amazing is that this quantization is extremely accurate. It's accurate to 1 part in a billion. It's surprising because it comes out of a device that looks like this. Okay, so this is a device that you make the samples as clean as you can, and the heroic efforts, but always some disorder, some dirt, and you try to rig up these contacts, and you end up getting something that's so pristine and so accurate. That was really a surprise. In fact, I believe now they're using the quantum Hall effect as one of the fundamental standards, and things like the kilogram are now defined in terms of this Hall resistance. Okay, so so that was the initial realization of the quantum Hall effect. It involved applying a strong magnetic field, but more recently, what has happened is people have been able to realize the same effect without any magnetic field. Okay, and here it really exposes this feature of the electronic bands of electrons moving through a periodic potential. And it was pointed out in this theory paper that there was this connection between a certain property of bands in a periodic potential and this quantized Hall conductance. And this was one of the pieces of work that was cited in David Paulus's Nobel Prize. And in fact, this kind of idea has been realized in experiments where people fill these bands, get insulators, but since the bands carry Chern number, they carry this Berry curvature, which integrates to some integer. You end up getting these insulators that have a quantized value of the resistance. You can get quantization 1, 2, 3, 4, and so on. Very accurately quantized again. But these are present even at 0 magnetic field. So this is 0 magnetic field. It's like a ferromagnet. And you can switch off the magnetic field and the quantization remains. Okay? So, so this is one set of phenomena where I would say that the crystal lattice has actually modified the propagation of electrons and made them behave in a way that they could not do in a vacuum. Okay, there's another very nice example, which is actually graphene itself. So in graphene, okay, so again, in graphene, this is a bunch of carbon atoms. Electrons moving through this periodic potential give rise to electronic bands that look like this. And at the natural filling of graphene, the natural density of electrons, you're right up here where these bands simply touch. And so if you examine how the energy changes with momentum, it's linear. It's like something that has a constant speed, very different from what you normally expect in semiconductors, for example, where you have a quadratic dispersion and therefore some kind of effective mass. Okay, so if I look at electrons that are at the natural filling in graphene and ask what is the equation that describes them, what is the modified Schrodinger equation? Well, the modified Schrodinger equation turns out actually to be a Dirac equation. Okay, so again, by virtue of moving through a crystalline lattice, you've modified the underlying equation, and not only is it Dirac-like, it's actually massless. So it looks like Dirac's equation, alpha dot p. Alpha are some matrices. Because they're in 2 dimensions, these matrices are 2 by 2 matrices. But there's no additional term that corresponds to the mass. Okay, and the wave functions over here are 2 component wave functions. The 2 components really correspond to the 2 sublattices of graphene. So if you look at graphene, it's actually a bunch of triangular lattices, but a pair of interpenetrating triangular lattices, the red and the blue. So if the electron lives on one of the red sides, it's a B electron, and if it's one of the blue sides, it's an A electron. That's what gives you the spinor structure of a Dirac equation. The other difference is that the velocity over here, compared to relativistic Dirac fermions, the velocity, of course, is much smaller than the velocity of light. It's as though it were a relativistic massless particle with all the velocity scaled down by a factor of 100 or something compared to the speed of light. Okay, so that's another qualitatively new effect. So the interesting problem that we are faced with when people did this exercise of taking a pair of graphene sheets and twisting them is we need to understand what happens when you have Dirac electrons, the Dirac electrons of graphene, moving through this this pattern, this periodic pattern created by the Moiré structure. Okay, so why was this interesting for people to think about in the first place? So it turned out there was some earlier theoretical work which had said that there's a particular angle in this for the system. It's about 1 degree, close to 1 degree. It's a very small angle. You just twist the sheets just a little bit. And when you do this, you get a Moiré structure, which is much bigger than the atomic lattice, okay? Because the twist angle is so small. The length scale that you get is essentially the inverse of the angle in radians. So 1 degree is about a 60th of a radian. So you get something that's 60 times bigger than the atomic scale of graphene. So it's about 10 nanometers. So what theorists had shown, a few years before, is that if you think about electrons, moving through this in this configuration, they take a certain amount of time to get from one Moiré side to the next. They have this velocity. They take some time, and if you have this particular angle, they take roughly the same time to get between the sheets. Okay, so there's some kind of resonance there. There's a kind of a resonance condition. When these 2 times are balanced, you expect something interesting to happen. And in fact, they had theoretically shown that the bands are very interesting in that particular case. Okay, so sorry for this slightly technical looking slide. The only thing this is meant to show is that the way in which the electrons see the Moiré potential or see the 2 layers is because they tunnel between the layers. Okay, they go from one layer to the next, and that's how they sense the potential. So it's a potential that's all in the kinetic energy. Okay, and this has different components. There are regions where the lattices are perfectly aligned, which correspond to one of these entries. There are regions where the lattices are displaced in a way called Bernal stacking, where you hop between sublattices, and that's these off-diagonal terms. There's a little bit of structure there that I don't want to get into, but if there are questions, I can tell you how this is related to the problem of Dirac particles in a non-abelian gauge field, because there's some very nice connections. But for us, what we want, what do the bands look like? The fact that you're moving through this new periodic potential means that you have to look at how the electrons, how the electronic states disperse in the small Moiré-Brillouin zone. Okay, so I said the unit cell is bigger. Go to Fourier space, everything becomes smaller, and that's this little Moiré-Brillouin zone shown over here. and there is some further degeneracy because of valleys that I won't go into. So so what the theorists have shown is that something very special happens when you go to the small angle of 1 degree. Okay, so if you plot what the band structure looks like, the energy as a function of crystal momentum within the small Moiré-Brillouin zone, you find these bands, they're dispersing, they kind of look like the dispersion of graphene's Dirac fermions, but there's this fragment that's left behind, okay, very close to zero energy, very close to where the chemical potential would naturally be if you're at half filling, if you're at the typical density of graphene. Okay, and these bands are,
sorry for interruption. What are the omega naught and omega 1? Are these the transition rates, something like that? Yeah,
exactly. They're the transition rates for an electron to make a transition from one layer to the other.
Okay.
They are roughly about 60 times smaller than the transition rate within the plane. Okay. And that's how you end up getting this angle of degree.
Okay, thanks.
So while we have you interrupted, what is the scale of the gap there? I can't quite see it on the picture.
Yeah. This scale is around 30 milli-electron volts. So if I were to convert it into Kelvin, it's about 300. It's about room temperature. This scale. But the dispersion is much smaller than that. It's at least a factor of 10 smaller. Particularly when you do it in this limit, you kind of ignore the interactions between the electrons. You just look at how much dispersion you get from just from the band structure. If you move off this angle, this very flat pancake becomes broad, and there's no significant structure. I'll show you a video of that shortly.
Just a small question. Now that you are there, you say it's sensitive to the angle, but also the separation between the two layers, right? Therefore, because
the separation you really cannot adjust. Yeah, you're right. It depends on the separation, but there's a natural separation when you put the layers together.
You mean this one that you talk about the time? You say only when the time of jumping from one layer to the other and the time to go to the Moiré lattice to the other. You said that? Is that the natural?
Yeah.
Okay.
Correct. Yeah.
But if you are there, if you are there and you have the 1 degree, then you get the zero energy. You don't get the perfect Dirac dispersion relation.
Yeah. So you can ask, it's a good question. You can ask if I can change the separation between the layers, I can change this W, and then can you change the angle? And in fact, you can. So people have done experiments where they press on these sheets. You can't really make them separate, but you can get them closer. So you can apply pressure and press on them and increase the W's, and then the magic angle increases, and they can see that. In fact, it's quantitatively very accurate. They know exactly where to go for each pressure that they apply. Okay, so this is what motivated these experimentalists, Pablo Herrero's group at MIT and his student Yuan Cao and other collaborators in 2018. They said, okay, let's go look at this system. Theorists had said, this is an interesting point. Go and look at 1.1 degree, but they hadn't said what would happen. Okay, generally we know that when you have electrons in very flat bands, the interactions between the electrons become very important. Okay, so by and large, when you have with some kinetic, it's really the kinetic energy that dominates over the. They modify things, but maybe not that much. But if you're in the opposite regime, things can really change. And that was kind of the motivation for the experimentalists to go and look. And what they found is sort of briefly summarized over here. So, one of the beauties of doing this experiment here is you can change the number of electrons in your system. You just gate it. You put a gate at the back and change the number of electrons. So you can take your chemical potential and sweep it through this band. And what that implies is, let's say you're below the band, then you've emptied out your system. When I say system, it's really this lattice, this Moiré lattice. At every one of those lattice sites, you can accommodate electrons. Okay, so it's a very small dusting of electrons, if you like, on top of the graphene sheet because the Moiré scale is rather large. So you could have no electrons there on that, no electrons relative to, say, charge neutrality. You can remove all the electrons, or you can add the electrons. And it turns out that you will get band gaps below and above. And you can do a simple counting and see that you need 8 electrons to go from below to above, where you completely fill everything over here. Okay, so you have 2 electrons, 2 spin up and spin down. That accounts for a factor of 2. There's a valley degree of freedom. That's a further factor of 2. And then there's another mysterious factor of 2 that turns out to be specific to these bands. It turns out that you actually have a pair of bands that are locked together, a little bit like graphene. So you actually have a further factor of 2. That's why you need 8 electrons to go from the bottom to the top. And these insulators are well understood. Okay. But what they saw in the experiment is there are further insulators. There are insulators in between as you're filling these bands. For example, here, you fill, there are 2 electrons per Moiré lattice site. And there's no way to get, put in 2 electrons without breaking some degeneracy, without having some kind of ordering. Either you pick a spin, or you pick a valley, or you pick a more complicated combination. So these insulators are clearly due to interaction effects. They're not something that you can explain simply at the level of 1 electron physics like we were talking about thus far. And then, of course, most surprisingly, what they saw was superconductivity as well. So you go near this insulating state of nu equal to 2. This is the number of electrons equal to 2. You go below that, you kind of dope it. So you're no longer an insulator, and you find that it's a superconductor. And the superconducting transition temperature is of order of a few Kelvin, 1 or 2 Kelvin. That came as a big surprise. Now, of course, you might say 1 or 2 Kelvin, we know many superconductors of that kind. Original superconductor discovered like 100 years back, mercury, a similar kind of transition temperature, lead, and so on. What's the big deal of a 1 Kelvin superconductor? Okay, but there are a couple of things that you need to factor in. One is that this is carbon, right? Just an element, carbon. It's not superconducting and it's by itself. But you put 2 of them together, twist them by 1 degree, it becomes a superconductor. Okay, so something else is happening over here. The second thing is, I told you that there's a scale factor of about 60 because of the small angle. 1 degree in radians is 1/60. So you can make a scaling argument that all energy scales should be multiplied by 60. If you want to make a fair comparison with another electronic system, like, for example, the high TC cuprate superconductors, you should multiply the energy scales by 60. Okay, so for example, this gap over here, we said it's about room temperature, it's about 30 millivolts. You multiply it by 60, you get 2 electron volts. That's roughly what the gap in the insulator and the cuprates is, for example. So those are kind of all those conversions seem to work roughly. And if you do the same for the transition temperature of 1 or 2 Kelvin, you see it's comparable to what people see in the high TC cuprates. So in a more reasonable way of thinking about the temperature, this is actually a very strong coupling superconductor. It's pretty amazing that it has that kind of transition temperature when you have such a tiny density of electrons being present, okay, effectively. So this was the experiment, and the challenge for theorists is to understand why are these things insulators, what is the nature of these insulators, what's the origin of the superconductor, okay, and so those are the questions that we got busy thinking about. But there's a third question which turns out to be extremely important, which is to understand the nature of these flat bands. Okay, and so one question that may arise is, we said this dispersion is very small. Is this engineering or is this science? Is this just very small, the dispersion, because you had this parameter, this angle that you could tune and you found a sweet spot? Or is there something more going on? Is there some reason why there's something special that makes it extremely flat? And it turned out that we found some answer to that first question, which I'll tell you about. And that turned out to also influence our thinking about what the insulator is. And then most surprisingly, by doing that, we were automatically led to a theory for the superconductor. Okay, so I'll try to describe that, but actually, Harsh, let me just check. How much time do I have?
About 20 minutes.
Okay, thanks. No, that's more than enough, yeah. Okay, so the first part is, let me tell you how we began to think about this, just the electronic bands. And we made an approximation which turned out to be very helpful. I won't go into the details, but we made what's called a chiral approximation. We threw out some of the couplings that take an electron from one layer to the next. And when you do that, you get a slightly bigger symmetry. And like all physicists know, if you have a bit more symmetry, things, life is a bit easier. Eventually, we put it back in, but this is something that gives you understanding and insight. So it's worth making this assumption. Okay, so we threw out this coupling, and then we asked, okay, what does the band structure look like as you change the angle? What does the dispersion of the electrons look like as you change this angle? So I have a movie over here that shows you how these bands change. Unfortunately, it's plotted in terms of this parameter alpha, which is the inverse of the angle. Okay, so the alpha is like roughly the conversion is about 0.6 divided by the angle in degrees. So at the magic angle, this is going to be about 0.55 or something like that. So just watch out as alpha comes down near 0.55. And they're starting at a large angle. Alpha small angle is large. You see at large angle, this is really just the Dirac cones of graphene. It's just been chopped up because I have a small Brillouin zone. But really that dispersion, everything is just that linear dispersion of graphene. It's not really affected much by the other layer. And the reason is that because you have a small, have a small Moiré pattern, by the time you go from one lattice side to the next, you hardly ever see the other layer. So nothing is really affected. Okay, so now let's play this movie and see what happens as the angle between the sheets is reduced, okay, towards this magic angle. Okay, so you can see these bands draw away and they're getting more and more flat. And then at this 0.59, it becomes very flat, and then it goes on. And it turns out that if you go below this first magic angle, you have this phenomena where it gets more dispersive, but then it comes back. So there's also some kind of second magic angle. And then you can continue, you can go on. There's actually a whole series. We had fun exploring these things. There's a lot of structure over here. We don't understand all of it. But the most important thing we found in this particular model was that these bands become very flat. But not just that. When we were doing this, so Grisha, who was the postdoc who was doing this, told me these bands look extremely flat. And as far as I can tell in Mathematica, they're completely flat. They're kind of mathematically flat. And in fact, we could show that in that particular approximation, this chiral limit, you can show that there's actually an angle where there is absolutely no dispersion. Okay, so this settles the question of engineering versus science. There's no way you can engineer the dispersion to be exactly zero at every point in k-space. You don't have that kind of number of parameters. You're just tuning one parameter. So this is really something new going on. And in fact, we could solve for the wave functions as well. You could do it analytically. You could find an analytic expression for these wave functions. That's maybe the subject for a different talk. But there's a lot of interesting math that appears over there. And some mathematicians have now gotten interested in understanding the wave functions and stuff like that of this chiral model. Yeah, is there a question?
Yes, that would be nice. When you say chiral, when I think about this system, I think in one layer I have the Dirac Hamiltonian with zero mass. Then chirality is a good quantum number to treat them. Then my Hamiltonian should have one in a layer, a second layer, and something that made the transition. When you say that the chiral approximation is good, is that you are thinking that this is a like small perturbation at this level, or something like that?
No, okay. So this has to do with certain terminology.
I am not a condensed matter person. Then this is why I try to follow.
Yeah. So this is a condensed matter terminology maybe issue. So first of all, these are two-dimensional Dirac fermions, so they don't have a chirality in the usual sense. But so the chiral over here refers to something else. So if you have a Hamiltonian that anti-commutes with a matrix, a fixed matrix in condensed matter, it's called a chiral Hamiltonian. So this is kind of a particle hole symmetry. It tells you if you have one energy level, there's one at negative. So don't worry about the word chiral. I'm just saying that
it's a totally different meaning. It's just when you take the Dirac Hamiltonian, you have the Pauli matrix there in your case, and therefore you can classify every term in this way. Okay, that's totally different.
Yeah, it's not as different as it sounds over here. So this, I think, this terminology is invented by Martin Zernbauer, who has a particle physics background. So there is some connection, but not in a useful way. I mean, not in a way that you can simply equate the two. There's another question. Is it Siddesh? Siddesh, did you have a question?
It's okay. I kind of you came back to the slide and it was answered.
Okay. All right. So now our problem is, we have the graphene's electrons. We added the Moiré lattice. That was this flat band we talked about. So now our next job is to talk about interactions. I'll do this very quickly because it's sort of hard to go into the details of how the interactions are taken into account. But the essential point is that by doing this chiral approximation, you get some insight into what the wave functions of the electrons look like. And there's a way to map this problem of graphene to a completely different problem. It's somewhat surprising that you can actually map it to the problem, the quantum Hall problem that I talked about before. Okay, so these flat bands, actually, it's one other place where we have these kind of flat bands are Landau levels. And it turns out that these there's a mapping to Landau levels, but they are doubled. Okay, of course, we've not added a magnetic field. So if there is a magnetic field up Landau level, there's also a magnetic field down Landau level. Okay, so they come together. That's one way to think about this problem. There's some additional degeneracy because of this valley I talked about. So at the end of the day, it turns out what interactions do is you have these different levels and you have to choose between them. Okay, you've got to pick a subset of them, and when you put the electrons into them, you can get an insulator, for example, at these other integer fillings. It's sort of very much like how you get, how you order the spin of electrons in a ferromagnet. Okay, so it's a generalized ferromagnet, and this is essentially our understanding of these insulators. But you can ask, is this like any other ferromagnet that we know about, or is there something special? And it turns out this combination of breaking symmetry and ordering in the presence of this band geometry or the band topology, the fact that you have these Chern numbers, they give you new effects. Okay, so let me briefly mention that. Okay, so this is just the same slide. It's just a way of rewriting these bands, and the symmetry breaking is picking one level over the other. Okay, it's kind of like ordering a spin. If the spin is up, you pick the yellow level. If it's down, you pick the black one. And there are two of these spins. It turns out that's the way to describe these insulating states. And when you order in this spin space, that corresponds to an insulator. Okay, so technically, it's like saying you have a sigma model. The ordered phase of the sigma model is some insulator, but there's something special about this this sigma model. Yeah, and actually that brings us back to something that was known in the context of the quantum Hall effect. I said that there was this early experiment where people changed the number of electrons in a Landau level. In this, when you have electrons in a magnetic field, you completely fill the band. You get the n equal to 1 state. But actually, I swept something under the rug. To do that, you have to pick a spin species. Okay, so you have to pick either spin up or spin down. And it turns out that the interactions between the electrons do that for you. They spontaneously pick either spin up or spin down. So it's a ferromagnet. And it's a ferromagnet that lives inside a Landau level. Okay, so again, you can ask the same question over here. Is there something special about this ferromagnet? And one thing you could ask is, what happens if I'd like to add another electron? Okay, so if I were to add another electron, there are two things that you could imagine doing. One is to pay the energy cost, go to the spin down band and add the electron over here. That's normally what you would do in any system. So to think about adding electrons, like what these experimentalists did, going away from the insulator, you really need to invoke this new degree of freedom, the new band. But it turns out there's another way of doing this for the quantum Hall problem, which was figured out in these papers, is that you can just make a spin texture. Okay, so this ferromagnet, instead of pointing up everywhere, can actually form a texture called a skyrmion. It's pointing up in the center, or rather, it's pointing down in the center. It's pointing up at the far away, and it smoothly interpolates between these two the directions, gives you this two-dimensional texture. And what you can show is that in this particular context, these skyrmions carry electric charge. Okay, and so then it becomes a competition. If I want to add electric charge, I can either go and add it up here as an electronic excitation, or I can absorb it into a skyrmion. Okay, and it becomes a question of energetics, which is lower in energy. And in the quantum Hall effect, it turns out these skyrmions are actually lower in energy. Okay, and that's been experimentally confirmed. There are these beautiful experiments in NMR experiments where they add electrons, and what they see is that there's a big downturn in the number of spins, because these skyrmions they flip many spins. They measure how many spins get flipped when you add charge to the problem. If you are simply adding charge one by one in the band above, you would expect this solid line. What they experimentally see is this these open circles where the spin drops a lot, and this is the theoretical prediction, the dashed line coming from skyrmions. Okay, so there's a context where these skyrmions have been observed. It really raises a very nice conceptual issue about what is fundamental. Okay, so normally we think of ferromagnet as being built out of electrons. So the electrons, they all order, the spins point in some direction, it gives you a ferromagnet. But here it turns out you can go in the reverse direction. You can start with this ferromagnet, and you can make this texture, this skyrmion texture. And in fact, that has all the same properties as the electron. It's a fermion that carries charge 1 and so on and so forth. So you can go backwards over here, and you can say the electron is a derived concept, and it's really the spin that is fundamental, at least in this topological setting. Okay, so the questions like this were studied many years back in the context of nuclear physics by Tony Skyrme, and that skyrmion comes from that. And he had a very interesting person, and it's kind of nice to read this paper. One thing I found quite interesting in this paper is that you look at the end, he has this little note at the end where he thanks this high school or this undergraduate student, I guess an undergraduate student, for doing the calculations. I think there's a typo over here. It's actually Tony Leggett, who was spending some time with them helping him with these calculations. So the next time you get an email from a student asking to do a summer project, maybe you should think about what happened over here. Okay, so I don't have too much time to get into this, but all I want to say is that something very similar happens in our problem. Okay, so we derived a theory for the insulator. It's a sigma model, and now I want to dope it. Normally, it would mean I have to introduce electrons, but because of these topological properties, you can just stare at that sigma model, the model for the insulator, and you can actually derive a theory for the superconducting region. Okay, so it's kind of, it's really asking for this kind of interpretation. And any theory of a superconductor should be able to predict the transition temperature. Okay, that's really the most important question. And our theory can do that. There is some bit of ambiguity what this coupling constant is, but it gives you a TC that rises linearly with doping and has the scale of a few Kelvin when you're at doping around 10%. So it's in the right ballpark, we'd say, for a theory of superconductivity. So I'll skip on and get to the real meat of this. So there's some intuitive ways of understanding the scale and so on, which I'll skip over. So how do we prove this mechanism, right? If this is really the mechanism for superconductivity, how do you go about proving it? That's a very hard question. People, for example, in cuprates, they've been debating mechanism for a long time. So what we thought we'd do is maybe we should try to predict a new superconductor. If you think you understand something, make a prediction. And one of the nice things about this mechanism is that it actually doesn't apply for many Moiré materials. Okay, so people have taken 2 sheets of graphene and twisted them. They'd also taken 4 sheets of graphene and twisted them. All kinds of combinations had been tried. But the one with the 2 sheets, the original one, was the only one where superconductivity had been seen, really in a robust way. I mean, the others, they had some signs, but not very robust. So we, to give a non-technical summary, there is a particular symmetry of the structure that we found, which is important for our mechanism. It's a rotation followed by time reversal. And so we decided that maybe that is fundamental, and we can try to look for new superconductors by applying that principle, that we look for systems that have that symmetry. So that's, of course, not a proof of the mechanism, but it gives you some useful prediction, which maybe is what we really want from any theory. So very few of these existing materials, but there's one family of material, one set of configurations where this is actually preserved, the symmetry. And this was also found in our group earlier. We were thinking about something else, and we thought about these stacks where you take a graphene sheet, you rotate the second one, and then you have a third layer, but the third layer is rotated back, so that the top and the bottom layers in the sandwich are actually at the same angle. It's only the middle one that's rotated. We called it alternating twist. There's also a 4-layer version of that where you go back and forth. And what Islam showed, who was the postdoc who came up with this idea, he showed that actually you have to do no new work to find the magic angles. Okay, so if you know what it is for 2 sheets, you can, just map the problem onto the same thing, and you find that for 3 sheets, there's also a magic angle, but it's square root 2 times bigger than the original magic angle. So instead of 1.1 degree, it's more like 1.55 degrees. If you go to 3 sheets, it turns out, again, there's another factor. Kind of interestingly, that factor is actually the golden mean. So the 4-sheet magic angle is golden mean times 1.1 degree. I have no idea where that golden mean came from, but that's what it predicts. But anyway, so the 3-sheet is the simplest. So what we did is we told our experimental friends, look, we have this theory, and we have this configuration. Can you look at 3 layers at 1.55 degrees and see if there's superconductivity, which is what our theory would predict? Maybe other theories would also predict it. So actually, this goes against some very well-established principles in condensed matter physics. So there was these rules that Matthias was, one of these old people at old Bell Labs people in the old Bell Labs who came up with looking for superconductors. He had this list of criteria, go to things that have cubic symmetry, a lot of electrons, don't look at oxides, don't look at magnets, stay away from insulators. So, he had these 6 rules, and amazingly, all 5 of his rules, the first 5 were broken when high TC superconductors were discovered. Okay, so high TC superconductors, the cuprate superconductors, they violate all the rules that went before. But there's a 6th rule that still held, which is, he said, stay away from theorists. Okay, so generally, if you go to an experimentalist condensed matter and tell them here's new superconductor, they follow rule number 6 and ignore you. But our 2 friends, Pablo and Philip Kim, they didn't do that. They decided to make these materials, which I thought was going to be extremely hard, but apparently not. They could do it, and they showed that this trilayer actually is a very strong coupling superconductor. Okay, and these are the 2 different papers that came out about a few weeks back, maybe a month back. I think one is in Nature, one is in Science. They show very similar phase diagrams as a function of changing the density of electrons. Again, the blue over here is the superconductor. The trilayer, turns out you have an additional knob, which is you can apply an electric field perpendicular to the layers. So it turned out very nice for the experimentalists. They can tune things. They can increase TC a little bit. It's up to 2 Kelvin, and it's extremely robust. Won't go into the details. And another thing is that they agree very well between the 2 experiments. So, this theory was helpful, at least to get to this point. But it remains to be seen, how much of these ideas are actually at play. But already, I think this is a lot of interesting ingredients in these systems from theory, and the fact that experimentalists can do these things so quickly and so reproducibly has been a great sign for the field. Okay, so let me stop over here, but I should acknowledge all of my collaborators, especially collaborators at Harvard and Berkeley, Islam Palaf, Shang, and Patrick, who worked on this, on the bilayer and trilayer, and our Berkeley collaborators, the group of Mike Zalatel. It's been a very nice collaboration with them. Also, we have several collaborations with experimental groups, and some of the prior collaborators are down here. Okay, so let me stop over here.
Great, thank you. That was amazing. So let's we have time for a few questions. Maybe we can. Okay, do you want to go first, Sudesh?
I was wondering about the you showed something about the bands being flat for the twisted bilayer if you kind of model it somehow without the diagonal terms of the Hamiltonian something.
Yeah.
So I think you also mentioned you also put it back and saw something well, were those bands still flat after that? After
yeah, that's a very good question. So it turns out, so if you remember, there were these sequence of magic angles, right? So this first one that we had, so it's over here. This is the first magic angle, corresponds to about 1 degree. This one, even when you add the diagonal terms, it stays very flat. So it's very robust to adding those diagonal terms. I don't have the picture there, but we have a plot of the dispersion as a function of adding those diagonal terms. It increases, but very, very little. If you go to the second magic angle, so you continue, you go further down, I think it's about 1/4 degree. There's a second magic angle that's predicted by this model. And for that one, if you go and add these diagonal hoppings, this one over here, you take this and add the diagonal hoppings, the dispersion is significant. So this one is not that protected. And we don't know if it has any physical relevance because the diagonal hoppings are not that small. But the first magic angle is very robust. So that's a bit of an open question. Why is it so robust from the chiral limit all the way to the realistic value?
Okay. Pavel, do you want to go next?
Better the students first, because I see students asking, and later I can ask.
Sure, go ahead, Mandela.
Thank you. Sorry, Pavel. Thank you for the nice talk. So early in the talk, you were showing the semi-classical equations of motion for an electron in a crystal. Yeah. And I think you mentioned that these were the most general equations we could write, something like that. I was wondering whether we could tell that from the form of the equations. I mean, should that be obvious?
Well, maybe I shouldn't say the most general. These are what certainly appear. If you have electrons moving in a band with Berry curvature, you end up getting this additional term. I mean, these we already know are there, right? These three are already there, and this additional one also appears.
No, so in principle, there's nothing stopping you from having new terms, right?
I mean, we should also ask the question whether there are corrections, in some, are they going to give you new physics or not, right? I'm sure there are new terms, but are there something in a gradient expansion that you would expect? Mm-hmm. So this is like the, this one, for example, you can show will give you a quantized Hall effect if you have, when you integrate this B tilde to be a Chern number. Mm-hmm. There are other interesting topological effects and bands that maybe are not captured by these. But yeah, this is to kind of make contact with something simple like semi-classical equations of motion of electrons in free space.
Thank you.
Okay, so Pavel.
Thank you so much for this. Is fantastic, very interesting. I don't work in this field, but it's fascinating. Huh? I have a question. I mean, I understand you see the superconductivity phase at the magic angle, but if you start from the beginning that you say I have the Dirac Hamiltonian for every layer, and I put the system together in this particular angle, why should I see that zero energy band there? you know, always there is a zero, you should think about a symmetry, right? Because it's very particular. What kind of symmetry can you imagine that can give you that? This is the first question.
It's not a, yeah.
And the second question is, could you say a little bit about no abelian gauge theory? You were talking about the application of abelian gauge theory. But the first question is, I remember talking to one of our colloquial speakers. He mentioned that people even thought about supersymmetry theory in this context, but I don't see the way to do something like that, right?
Yeah, I don't see anything to do with supersymmetry, right? But the non-abelian potential I can explain is very simple, actually. So if you just go to how this the electrons experience the interlayer potential, this is what it looks like, you know, so this is actually a layer index. So this T is, you know, if you write down the full matrix for the electron, there are terms that are diagonal in the layer index where the electrons live in the same layer, and there's a term there where it goes between them. Going between them is this one. So it's off diagonal, and you can show this additional index that you have, the layer index. You can think of it as an SU2 gauge index. And then you write out the terms, and this looks like, of course, it's fixed. It's a fixed potential. It's not fluctuating. It's not a fluctuating gauge field. It's a background field, but it's SU2, and it's non-abelian. It's intrinsically non-abelian. And you can show that you need the non-abelianness to get the flat band.
And can you generalize that for multi-layer, that you will get a SU3, SU4 if you start putting 3 layers? You will get maybe SU3 gauge theory. You can apply that. That's pretty cool.
Yeah, I don't know if it's helpful, but this the thing that is helpful to think of it in terms of SU2 gauge field is you can identify this condition that it has to be non-abelian. If you can abelianize the gauge field, you don't get the flat band. That's something we don't understand. But yeah, it's.
So I guess in light of the time, I'm going to switch over to informal discussion. But please, everybody, stick around if you have questions, or if you just want to hear the exchange. But we'll end the formal proceedings here. And I have to say, this was an incredible talk. I mean, this may be the first time anybody's predicted a strong coupling superconductor, to my knowledge. So, it's fun to be among the first to hear it. The unfortunate thing is that Zoom doesn't really allow us to show our appreciation. So we'll just do some lukewarm applause, and then we'll switch to the informal section. Okay, so there's a couple of questions that were from the formal session, maybe Walter and Shule in that order, and then we can really break up into just discussion.
Okay, so I was just wondering what's the physical meaning of these diagonal terms that you left out? Because to me, it looks like, you know, it's the same on each diagonal. Why can't I just take that as my reference? Maybe I'm missing something. You know, I mean,
it depends on R. It depends on the position.
Symmetric. Okay, so this is 0, but it's different at each position on the surface.
Yeah.
Okay.
Yeah. So it changes the band structure. Yeah.
So that has something to do with this Moiré pattern ultimately, right? How they.
Yeah, exactly. Yeah. This is the period. Yeah.
I see.
Yeah, these functions U0 and U1, they have their periodic functions, and their period is the Moiré period.
But okay. So while we're thinking about this thing, so this A and B still refers to the 2 positions in the graphene lattice, right? But I also have 2 layers.
Yes.
So why isn't there a 4x4 matrix needed?
It is 4x4. Yeah, it is 4x4. So I don't know if I can find. This is the colloquium version of it, but I think maybe it's more clear if I show you the non-colloquium version. Let me find it. Just give me a second. Let me put it.
Yeah, it has to be 4 by 4 because every layer is 2 by 2. Dirac Hamiltonian is 2 by 2, and then you have 4 by 4 there.
Yes. Okay, so now let me slideshow window, share screen. I have to do that again, right? Yes.
Yeah, you should be able to, yeah.
So this is, let me just go over it a little more technical. So that's the twisting in the momentum space. It gives you the Moiré-Galois zone. And this is what the Hamiltonian looks like with the layer index in place. So there's this term that lives on the layer 1. This is the term on the layer 2, Dirac particles. And then there are these T's that are off diagonal in the layer. That's what couples the electrons between the layers. And T itself has a structure. It has a 2 by 2 structure because of the A and B sublattice of the graphene.
Right.
So this, so this term over here, the diagonal term, they correspond. So this is what the Moiré looks like. So there is, you can take an origin where the two layers are kind of right on top of each other. They're kind of occluding, the atoms are occluding each other. The hopping in this region is called the AA hopping. That's this W naught. Then if you move through the Moiré pattern, you'll find another region, this yellow region where it's called an AB region. It's like one of the atoms is occluding one of the atoms in the other layer, but the others are not, or the two are not. That's called Bernal stacked graphene. That's the this off diagonal, so AB tunneling. So this, as a function of position, is just reflecting the strength. So for example, W naught is large in this region of the Moiré, and it's small over here. It's large again over there. That's how you get the periodic pattern. And AB is large in the yellow region, but not in these other regions. So that's how you sense the Moiré potential in this problem.
Right. Thank you. So when you were showing this movie of the band structure changing, that was just done numerically with a big model.
Yeah.
Okay.
Yeah, with this model, just solve this model on a
you can
computer.
kind of do it analytically. Oh, okay, I understand. Thank you. Very nice.
So you can only find the zero energy states analytically. So when this thing goes and it becomes zero energy, then you can find it analytically, and you can show it's a ratio of theta functions.
I see.
And yeah, but as soon as while it's like one of these problems where it's easier to find a zero energy solution than a general eigenvalue.
Right.
Because you can do half the matrix when you're doing a zero energy solution, but the matrix is not a Hermitian matrix. So you're not guaranteed a solution.
Sure. Yeah.